All right. So for this talk, I'm going to present some of my recent work using particle filter-based strategies for actual numerical weather prediction applications. And so just to begin, a quick recap of the seminar on Tuesday was first what I did was introduce this Bayesian filtering problem, which is just a generic data assimilation. And so the goal is to estimate a model state's probability distribution conditioned on some measurements. And we have our state vector, which we're going to call x, which is of size nx, and our observation vector y, which is of size ny. And x contains all of our state variables or model variables, y contains all the observations. And x is propagated forward in time through a nonlinear model, M. For the case of weather prediction, it's a full weather prediction model, and including the Navier-Stokes equations, thermodynamics, various physical parameterization schemes. It's a pretty complicated model, and of course it's imperfect, and so we have this error term for each step, and observations are related to the model state through this operator H. And so that can be things such as radiances, which are most of the measurements we have for the atmosphere on the synoptic scale. All right, and the filtering density is given by Bayes' theorem, which I'm showing here. And it is just saying that if we have some prior probability density for x, which is conditioned on past measurements of this system, all we have to do to estimate this conditional probability that we're after for this univariate example I'm showing here is just to multiply this PDF by the likelihood for the new measurements that we're introducing. And this normalization here is just so we have an actual PDF when we're done. So this just normalizes this part. And the prediction step is given by this integral here, which transitions this posterior density to our forecast, or we could just call it our forecast PDF, which I'm showing right here. And it tells us something about essentially what's going to be the prior for the next step of this Bayesian filtering process. And so this is mathematically how you represent that. But of course, we can't really do this directly for big problems, and so we have to apply approximations. One of which, of course, is to apply a Monte Carlo approach. And so for Monte Carlo, the data assimilation part comes down to trying to sample from this conditional probability distribution. And once we have these samples, we can pass them through our forecast model, and the results are samples from this forecast error distribution that we're going to use for our next prior. And of course, for weather forecasting, we call this an ensemble forecast technique, and we use it to come up with estimates of uncertainty in our predictions for the atmosphere. Good example is right now it's hurricane season in the U.S. and ensemble forecasts are very beneficial for coming up with estimates of where the storms may go, whether or not to evacuate various parts of the East Coast because of tropical cyclones, and also determining what the potential is for intensification of pre-existing tropical cyclones. And so these ensemble forecasting techniques are quite useful for decision makers for severe weather events such as this one. And on Tuesday, we talked about particle filters and how they approximate these densities that we're after. And so just to provide a quick recap, in the context of data assimilation schemes that we currently use for geoscience, which include ensemble Kalman filters, what we do is we apply this Monte Carlo approach and use the samples to estimate a mean and error covariance for the variables that we're after. And so that's all we need to come up with a Gaussian representation of our quantities. For particle filters, we replace this Gaussian estimate with a simple direct delta function estimate. And of course, this method has some advantages, but also some major problems. One is that your solution here no longer has positive probability in the tails like we have here for the Gaussian. And so the potential for this method to collapse is pretty high. You also need a really big ensemble, and so there's a lot of negative and positive properties of particle filters. The advantage here, though, is even if we have a nonlinear forecast model, a nonlinear measurement operator, and non-Gaussian errors for all the various parts of our system, this approach will converge to the actual Bayesian solution, so long as we have a really, really big ensemble and we have a perfect handle on these errors. And what I mean by that is we have a perfect representation of our model errors and observation errors, which of course is impossible to do, but this is just a goal that we should have, is trying to get a good handle on these errors. Like ensemble common filters, you need really big ensembles. These methods don't scale as well as ENKFs, but ENKFs also still have scaling problems for big data simulation applications. And of course, just like for ensemble common filters, we need to apply some approximations to make particle filters applicable to high dimensional problems. And so for ENKFs, what we've done in the past for numerical weather prediction is apply things such as covariance localization, inflation, and regularization. And for particle filters, you can do similar things. And here's just a nice summary, a nice review paper by Peter Yan and a bunch of other people in the particle filter community that discuss some of these. All right, and on Tuesday, we discussed a strategy for trying to sample from a localized posterior density estimate from a particle filter. And I discussed what localization meant in the context of particle filters. All it means is you want to try to apply this particle filter strategy for discrete parts of your state space in a way that's independent from other parts. And so you're essentially exploiting the fact that for these big geophysical problems, that the dynamics are rather sparse, at least over short time scales. And so what you can do is break this big data simulation problem into a set of independent problems that we can solve independent from each other. And so the strategy I adopt for this localized particle filter approach is to assimilate observations either one at a time or in batches. And so what I'm going to do is apply a serial set of update steps that looks a lot like we apply for serial ensemble common filters. And for a given batch of observations or single observation, the idea is to transform prior particles so that the obspace representation of this PDF looks like a particle filter approximate. And so an obspace for each of these iterations, you're going to essentially just have the particle filter estimate of that PDF. And in model space, which is much trickier, the goal is to just match different marginals of this localized probability density that we defined on Tuesday. And that means just the mean variance and even higher order moments. And so because of the sampling step in the first part, that's how we're treating the multivariate problem. But we're not really matching direct multivariate estimates from this localized PDF. We're only trying to match the marginals. All right, and so the motivation for this type of work comes from the applications that I'm interested in for my own research. And so I am a meteorologist. All my degrees are in meteorology. I've spent time at two national labs in the US, namely the National Severe Storms Laboratory and the Hurricane Research Division of the Atlantic Oceanographic and Meteorological Laboratory. And I'm still an affiliate of this lab right here. And the main focus of these two labs in the US is severe convective storms at NSSL and hurricanes at AOML. And the current data simulation strategies we have for these problems can be quite suboptimal because they're quite nonlinear. Both of these applications depend on very nonlinear cloud processes, and so that complicates things quite a bit. The observations that we have often relate nonlinearly to the model state variables. A good example for the convective scale is radar reflectivity, and for tropical cyclones, most of the measurements we have come from radiances, which are just measured from satellites. And also because of advection in our governing equations for the atmosphere, we have displacement errors in various features, whether it's clouds or even large-scale features in our system. And I'm going to show a demonstration later on that demonstrates why this leads to pretty non-Gaussian prior PDFs for data simulation. All right, and so I'm going to break this talk into just two parts. One is focusing on my recent work on severe convective storms, and the other is on tropical cyclones. And both of these, I would say, are just a work in progress, using some of these new nonlinear particle filter-based data assimilation techniques. And so for the first part, severe convective storms, this is a really tough application because for one, errors in initial conditions can go really, really rapidly. We have low intrinsic predictability. I'd say the best forecast right now for severe convective storms in the U.S. are only accurate within maybe 30 minutes or so of model initialization. And this corresponds with the time scale of individual clouds in our system, which is about 30 minutes. And the best we can do right now with our current computing resources is perform sequential data assimilation every 15 minutes. We have some research tools for doing this at a higher frequency, but operationally we're looking at about 15-minute updates. Also, large model error. Predicting the evolution of severe convective storms requires a accurate representation of moisture and various cloud processes, radiation, turbulence, and other things that are just parameterized in our current weather models. And so there's a lot of model error involved in modeling these dynamical systems as well. And most of the observations we have for thermodynamic variables comes from radar reflectivity, which relates nonlinearly to our model state variables. And so that causes some trouble as well. All right, and so the best way to demonstrate some of the issues we have, at least on the side of nonlinearity, is to just show a simple example. And what I'm showing here is an example of what happens when you try to assimilate reflectivity measurements to update cloud variables in our model. And so this is a perfect model experiment, and so this is not a real case. So what I did was I just ran a simulation, generated my own radar reflectivity observations from it, and went back and assimilated those observations back in for an ensemble set of ensemble data assimilation experiments. And what I'm showing here on the left is one snapshot in time of my truth simulation. And at the start, we have a reflectivity measurement. And so this right here is just going to be a horizontal cross-section through these convective cells. And right here is a vertical cross-section where these dashed lines just correspond to the respective cross-sections. And for our prior, we have 100 members or particles that are supposed to just be equally likely samples from our prior error distribution. And I'm showing the first 25 of these on the right over here. And so the goal is to come up with a posterior estimate of cloud properties based on this prior and this observation right here. And so the best way to visualize this is to first just look at what happens in observation space. And so here what I have is an observation, a joint ob space model space distribution. And so on the right, what I'm showing, I'm on the left here. What I'm showing is scatter plots of on the x-axis reflectivity. So these are my ob space priors, and on the y-axis the different cloud variables that are going to be updated that are co-located with this observation. And so these are mixing ratios of ice, rain, snow, and graupel in the model. And so different hydrometeor species that are characterizing the clouds. And you can see these distributions can be really, really crazy. They're definitely not Gaussian. They're bounded at 0. And they have some pretty complex relationships going on here between different frozen species and just rain and how that corresponds to different reflectivity that we're actually measuring. And so if you go ahead and you use an ENKF to update those members based on the observation, you get something that looks very unphysical. And the first thing you notice here is for a lot of these mixing ratios, it's going to draw members in areas where you have negative values for mixing ratio as a physical impossibility. And in practice, what usually occurs is the data assimilation system will go back and zero these values out afterwards. Also, more importantly, what's happening is you're drawing various species of ice into areas where it's just unphysical because of because of the constraint of temperature on ice as well. And so you have zero prior probability in some of these regions just because they're physically impossible. And so that could be problematic, of course. And if you were to apply a particle filter for this, it's not going to have the same issues. But then you have to, again, go back and worry about updating the rest of the state variables in your system, and also worrying about the dimensionality constraints of this system, which is why we have to apply some of those localization approximations, which I went over on Tuesday. But at least in observation space, or in the vicinity of observations at least, you have a pretty nice particle filter looking solution that's not going to cause a lot of these issues. And so what I did in a paper that I wrote in 2017 is to apply a series of data assimilation experiments using that localized particle filter with the ensemble adjustment common filter. And what I'm showing here is the evolution of my truth. This is just what I used for the first demonstration. And what I did was I went back and I simulated reflectivity measurements sampled from these convective cells every 5 minutes, and I simulated them back into the system. And what happens is you have these individual cells that evolve into this more organized system with time, which is called the mesoscale convective system. And I'm going to show some real cases of this in the next several slides. But I would say that the important result here is when you apply an ensemble common filter for this application, what happens is it gives you really, really large biases in the moisture field. And that comes from the update of hydrometeors based on these reflectivity measurements. And it has some pretty big impacts on the forecast skill of this method as well. And so on average, the particle filter produced more skillful forecasts for this event, for this idealized simulation because of this. And so what I'm showing right here is bias as a function of height for the particle filter or local particle filter in blue and the EAKF in red. And of course, you do have some bias from the localized particle filter because the localization itself is going to introduce biases, but it's not nearly as bad as the ensemble common filter. And this is an important finding because it means that you can get pretty substantial biases just from the data assimilation method for some of these applications. And if you're a model developer and you want to say something about like say the microphysics or some other part of this model, you may think that these issues are caused by the model itself when in fact it's actually an issue with the data assimilation. And I'm going to start picking apart some of these issues for real cases with an NSF grant that I have right now. All right. And so after the idealized case, I went ahead and ran a couple experiments for real cases using this research to operations modeling framework, which was built at the National Severe Storms Laboratory of NOAA. And so the framework looks like this. We have these sets of model domains. This blue domain right here comes from one of our operational models that's run in the US that assimilates observations every hour. This green box right here is the box that we run this experimental system in, and so it takes boundary conditions from the model domains represented by the blue boxes, and assimilates observations every 15 minutes. So whereas the operational system that it's using does data assimilation every hour, and so the way this works is it grabs model solutions at 18 UTC every time there's a convective outbreak in the U.S. And they run sequential data assimilation until 3Z the next day. And I'm going to show 3 different cases using this system, comparing this new localized particle filter with their current data assimilation system, which is the ensemble adjustment common filter, which I mentioned earlier, using the NCAR data assimilation research testbed. This is all done using a very small ensemble, so they can only afford 36 members for this, and so it's a tiny ensemble for an ENKF. Let alone a particle filter. And this, of course, is very challenging because these convective cells have pretty large degrees of freedom. We're not representing a lot of the physical processes well, and model and observation errors are also not characterized very well. And what I'm going to show is first this initial case, which was a pretty damaging event in the U.S. And so it is a severe convective outbreak that produced several tornadoes over the central U.S. And so the The actual tornado reports are shown here by these red markers. And we also have reports of high winds and hail and other events. And so I'm going to compare this local particle filter with the EAKF for this complex case, which I'm going to show on the right here, in which we have these multiple cells that form and merge together into a squall line, just like this demonstration I showed earlier. And so this is done over that whole cycling period, which I showed on the previous slide over here. And so this goes from 18Z to 3Z. And what I did was I ran data simulation experiments and generated 90-minute forecasts from the different methods every 30 minutes along those that schedule. And so for verification purposes, what I did was I took all the radial velocity observations we have over our domain. So here are the radar locations across the U.S. And here's our domain. And here are these radars in the domain. And I'm going to use the velocity observations to verify the flow field. And I'm only going to do this for the ensemble mean. And so what I'm going to do is run ensemble forecasts for these different cycles, and just calculate a mean for the ENKF and particle filter, and calculate a root mean square fit to the observations, and use that for verification purposes. With 36 members, you cannot really say much about any high order moments, and so I'm just sticking with the mean. And so for the first case, I'm showing the verification on the left. And so I'm showing root mean square fit to observations for the ENKF, red and blue particle filter. And these dashed lines are just the expected errors. And so it's a function of your ensemble spread and observation errors. And results, of course, are averaged over all these forecasts that I ran. And the reason why you have the zigzag pattern is because of different scan volumes that are coming in at different times from the radars. And so that produces this choppy looking result. But this is for the first case, and we were pretty happy that it was comparable to the EAKF. I personally did not think that this method would work, as well as the ENKF for a problem like this, which is 36 members. So that was exciting for me, and we went ahead and applied this method for 2 more cases. The first is a case where, again, we have convective cells that grow upscale into an organized mesoscale convective system, and on the right I'm showing a case where we have long-lived tornadic supercell across the domain. And so this is an easier case because there's a single cell event, whereas this one involves multiple cells merging together. And because of the dynamics of this case, where you have things such as cold pools that form below the individual cells, and density currents that are going to collide and cause some interesting dynamics, like this is a very complicated case to deal with. And so on the left, I'm showing the same verification for the ENKF and the local particle filter, and it's nice that I could at least get some improvement for the particle filter for this case, and the results are similar for the single cell case. And so we only applied these methods for 3 cases so far. There's ongoing testing right now at NSSL and University of Oklahoma to apply this particle filter for more cases in the same exact framework. And the idea is again to use it for to see if they can replace their current ENKF with this particle filter for their research operational system, and also learn something about the dynamics as well. And so one thing I'll mention here is the solutions for the ENKF and particle filter look very different, even though the forecasts are actually comparable. And so what I'm going to show here is if you were to look at the observation space estimate of these convective cells for the ENKF. Here are the first 10 members, and here on the right is the actual reflectivity. And they all look very similar. I mean, they all match up with the observations quite well. And here is the same result for the particle filter. And the particle filter members don't necessarily look at all like the observations, but they do look like the WRF model's representation of the observations, which include all these biases in them. And this corresponds to biases in the microphysics scheme that they're using. And so if you look at and go back to the ENKF, you see this big adjustment that occurs in the individual cells over a short period, just because you're fitting the observations really well, but you're not actually updating your model variables in a consistent way. And and some may see that as a negative result for the particle filter, but I actually see it as a positive because it tells us something about the microphysics schemes and where we have these biases that we have to fix. And so this is leading into some of my current work, which is using these particle filter methods to try to uncover biases in models. Given that we can isolate biases from data simulation from the models by solving some of these nonlinear problems, then we can say something more about the models themselves. All right, and so for the last part of this talk, I'm going to discuss some of my recent work on tropical cyclones. And this is work that started at my last postdoc appointment, which was at the Hurricane Research Division of NOAA AOML. And so for this application, it's quite challenging because one, it requires an accurate depiction of many scales of motion. And so hurricanes are these big multi-scale weather systems that are really hard to predict. They involve both convective scale motions as well as the synoptic scale. And so synoptic scale is wavelengths that are greater than or equal to 1,000 kilometers. And so you have to run really big model domains for these events. Model error is also a problem, just as before. It's not as bad as the convective scale, since a lot of the important processes are resolved, but it's still there. And also another issue is tropical cyclones occur over the open oceans. And so that means we just simply don't have as many measurements. And so many of the important mesoscale features, so wavelengths that are about 100 kilometers or less, are not constrained by observations. And so I'm going to show why this is a problem at the end of my talk. All right, and so the work that I've been involved in on this is it started from just one of our operational systems in the U.S., which is called the Hurricane Weather Research and Forecasting Model, and the domain is showed right here in this picture, and this model runs by initializing this parent domain right here off of our global forecast system, or GFS, and it also initializes two inner nests that go down to 1.5 kilometer grid spacing. And this is centered on the tropical cyclone vortices, and it moves with them. And so as the storm moves, these nests move. And down here in the bottom, we have a experimental system that is run at the current lab, or the lab that I was in for my postdoc. So this NOAA AOML. And it looks a lot like the operational system, except they have these multiple nests, multiple nested domains that can move around with storms. And both of these they're sophisticated modeling systems, but they don't have sophisticated data simulation. In fact, like this one just initialized off of GFS, and some data simulations performed on these inner domains, but that's about it. And for this one, there's no data simulation at all. It's just completely initialized off of GFS. And so for my project, I transitioned this operational system into a fully sequential data simulation and forecasting framework that we can use for data simulation research, and also learning something about the models as well. Just performing data simulation in any model should reveal biases and other problems in your system, and so it's a very important practice. And so this the system that I started when I was there is I have a video showing it working, but it's not working for some reason. It's essentially just taking, I'm going to go back a slide, taking this basin scale HWRF system and performing sequential data simulation over this big area right here, and just running it nonstop for entire tropical cyclone seasons. And yeah, this video is not going to work. And what I'm showing here is contours of pressure, and these colored values are increments made to the 850 millibar vorticity field to show you how the measurements that we have are making corrections to synoptic scale features in the system, as well as position intensity of tropical cyclones, which are indicated by these tropical cyclones and tropical waves, which are indicated by these different letters. Some important details about the system. It's an experimental framework that is based on this hurricane weather research and forecasting model. We apply sequential data simulation over a extensive region using the ENKF and the local particle filter to simulate measurements that we have every 6 hours. And it uses the same exact observations as our operational global system. And so what we're trying to do is mimic as close as possible what we do for global numerical weather prediction. And the reason why we want to do this is because, one, this is a regional model that's used a lot in the U.S., but nobody really understands some of the bias characteristics associated with it. And so it's important to go and test it out in this framework. And also, we want to have a nice, affordable framework we're doing satellite data simulation research with, especially pertaining to tropical cyclones. And it's really tough to do that with the global system because of the computational cost involved. And this is all done using community software that's available in the US for data simulation and modeling. And so all we did was take the operational HWRF system and add a bunch of flags in the code so we can shut off various parts and run sequential data simulation. And this is all built right into the community software that's available. And so it advances in the code alongside all the advances to the actual model itself. And so anybody can go and use this framework. All right, and so let's get back to the actual problem at hand, which is the nonlinear, non-Gaussian DA problem posed by tropical cyclones. And so this is going to be the example I showed on Tuesday for the position displacement error issue. And so as I mentioned earlier on in this section, one of the big issues with tropical cyclones is a lot of the mesoscale processes involved are not depicted well by observations. They're just not constrained by the observation networks that we have for these systems. And so you can have pretty large displacement errors in any mesoscale vorticity anomalies or so below about 150 or 200 kilometers. And you're going to see this in the results when I go back and look at the real case with this system. And so here what I'm doing is I'm just mimicking a common problem in which we have some displacement errors in a vortex. And I'm showing just 5 ensemble members for 850 millibar height, and just from a subset of an ensemble forecast from a 6-hour ensemble forecast. And so this is a typical displacement error we would see for say, tropical cyclones. And I'm going to reproduce this problem using a ranking vortex model. And what I'm showing here on the top panel is the model wind profile. And so I start off with something that has a value of 0 at the domain center and increases linearly out to a radius of max winds to this point, and then decreases exponentially away. And taking this profile and putting it onto a 2-dimensional grid, and just doing this extrapolation from here to here gives you this picture. And what I'm showing is wind speed every 15 meters per second for these 2 contours with values greater than 15 meters per second in this hatched region. And then taking this profile, putting it into this domain, the next step is just put it onto a Cartesian grid. So it looks a lot like the variables that we use for weather models. And so they're defined by horizontal, the winds are defined by horizontal and meridional winds. And so we call them the U and V components of wind. And so our model state here is going to be given by x equals this vector, which has these 2 column vectors here, u and v, where u and v is just the components of wind at each grid point in the system. And then what I'm doing is reproducing this vortex displacement problem by perturbing a set of vortices and calling them my ensemble members or my prior members. Since I have 100 vortices here that have identical structure but some position error associated with them. And I simulated some observations from a designated truth. And these observations are radial wind observations. And these are the best observations we tend to have for tropical cyclones. In the US, we fly planes right into the storms, and we collect these measurements. The issue here, though, is that you're only usually observing maybe like a portion of the storm at a time. And so it's typical to within a 6-hour cycle only observe maybe like 1 quadrant of the storm, which I'm showing right here. And the application for data simulation here is we have to update all the state variables in our system, even variables that are on the other side of this domain, which is going to be problematic. And for the ENKF, this problem is quite difficult because the underlying air distributions are quite non-Gaussian. I'll show some illustrations of that in the next couple slides. And for the particle filter, for the localized particle filter, it can do a little bit better on this problem because it gets around this non-Gaussian data simulation issues that we have for the common filter. And as I mentioned in my tutorial on Tuesday on this localized particle filter, it uses localization regularization to prevent all the numbers from collapsing to one solution. And it does that in a way that still preserves some of the useful properties of particle filters for problems like this. All right, and so to understand what's going on here, just recall that that in order to estimate these u and v components of wind in our state vector, we have to infer something from the joint OBS model space statistics that we have on this system. And so what I'll do is I'll just take a point A right here and grab one of those radar velocity observations and project all the members onto that point and call that my OBS space prior for this point right here, or UR at A. And then what I'm going to do is look at what the model space variables for U at point B look like, and see what this joint PDF looks like from large samples to get an idea of what that distribution looks like for a case like this in which you have these displacement errors. And so what I'm showing here are those values plotted for 4 different configurations. On the leftmost panel right here, I have on the x-axis the OBS space prior, and so this is just projecting those winds onto the observation onto the observations that we have. And on the y-axis, I'm showing the u component of wind at point B, and then what I'm showing by these gray contours right here, if I were to just form a Gaussian kernel estimate of the marginals for each of these, this is what it looks like. And so this is for a case in which I have sigma p over r, which is where sigma p is just the standard deviation in position error for the vortex, and r is the radius of max winds. And so you can think of it as like a size parameter. When this ratio is about 0.25, you get a distribution that looks like this, and when it's about 0.5, it looks like this, and all the way to 1. For most cases, this ratio for tropical cyclones is somewhere between this value and this value. And for the last column, what I'm showing right here is if I have the same ratio, except I also include some uncertainty in size and intensity for the storms. And so this is more like a realistic case in which you don't have just position error, you also have errors in the size and intensity of the vortices as well. And so the point of these here is one, the dominant error is obviously position, and it produces some pretty non-Gaussian multivariate PDFs. But at the same time, the marginals themselves look pretty Gaussian. And so if you were to just look at the marginals, you may think that this is a pretty Gaussian-looking problem, but really it's not. You have to consider this whole multivariate PDF. And for an ensemble common filter, what would happen is if you want to make an adjustment in your OBS space that goes to the right, what's going to happen is it's going to move all of these markers down this way along the error correlation line, and it's going to take the values in the tails and pull them into areas of the probability space that are non-zero. And that's why you get those big asymmetries that you see for the E and KF case. What it's doing is it's just simply pulling these markers in areas that have zero probability, because it's making the Gaussian assumption on these this joint distribution. All right, and let's see, I'm going to skip ahead. All right, so with that, I'm going to move forward with a real case. And again, my videos are not playing, which is okay. I'm just going to describe what they would be showing up here. And so what I have here are contours of mean sea level pressure in red, and I have markers indicating the actual observation locations. On the top, I'm showing the locations of what we call conventional observations, which are going to be things such as in situ measurements over the U.S. coming from airplanes, also ground stations, buoys and ships in the ocean, and cloud track wind vectors over the ocean as well, which are just coming from atmospheric motion vectors backed out of different radiance channels. And at the bottom here, I'm showing all of the locations of radiance observations that are collected over this domain and assimilated into the model. And all these different colors indicate different types of satellite platforms at different times. And so if these videos were playing, they would show the evolution of these model variables and our observations over a whole month. And so what I did was I performed some data simulation experiments over a whole month using this experimental regional modeling framework. You'll notice the domain is a bit smaller than the one that I showed earlier. And the reason why is because the domain that we were using earlier was something we ran in near real time during the hurricane seasons. And on the fly, as we were doing data simulation, we were calculating biases for clear air radiances that were used to bias correct the measurements. You need a pretty big domain to do that, and then we stored those bias correction coefficients. Then we went back and did some numerical experiments with a reduced domain size, but still using those same bias correction coefficients in here. And so that allows us to simulate the radiances properly, but still use a relatively modest size domain. And what I'm going to show here is some experiments using a model configuration that looks like this. And so I have a model grid spacing, which is about 18 kilometers, which is relatively coarse for tropical cyclones, but it's about the same, comparable to grid spacing used by global models. Observation frequency of 6 hours, just like the system we use in near real time. And we have two different ensemble data simulation schemes. One is the Whittaker-Hamel ENKF, which is used operationally in the US, and a variant of this Poterjoy et al. 2019 particle filter, all using an ensemble size of 60 members. And so this is all done using the operational data simulation package that we use in the US, also called the Grid Point Statistical Interpolation Package. And for verification, what I did was I ran 5-day forecasts out from my cycling data simulation experiments. And I did this for a 20-member subset of ensemble members every 12 hours. And I ignored the first 5 days of sequential data simulation to let the method spin up. And I'm showing at the bottom right here the area that we verified. We're ignoring grid points around the boundaries. And we're just doing some verification over this hatched region right here. And what we're using as our verifying truth is the global forecast system analysis, which is a 4-dimensional data simulation solution that's produced every 6 hours. And just a quick verification, what I'm doing is I'm verifying the ensemble mean again of these forecasts. And the blue values are the particle filter, and the red is the ENKF. And we're actually providing some benefit over the ENKF over this month-long experiment using this localized particle filter. And again, this is our first stab at applying this method for the synoptic scales. And one thing you'll notice is at the beginning of the experiments, they provide comparable forecast results. And in fact, the particle filter has less of a match to the GFS analysis of the ENKF. And the reason why you get this result is pretty interesting. I'll talk about that in a moment. And that's for U and V wind. Here's temperature and specific humidity, and vertical vorticity and mean sea level pressure. And so for all the metrics we looked at, we found some improvement in skill for this localized particle filter over the ENKF. But as I mentioned, the reason why is quite interesting, at least in my opinion. And so what I'm going to do is pick apart how these different methods update the wind field. And so the way I'm going to do that is first consider what the vortex power spectral density looks like for H-Whorf model. And so what I did here was I produced an average power spectral density for the vertical component of vorticity by calculating the power over all these different wavelengths, going from over 1,000 kilometers down to about 30 kilometers, and or 40 kilometers, and average the results over many 24-hour forecasts for all the different members from the ENKF experiment in red and particle filter experiment in blue, to get a sense of what the climatology looks like for this model for the wind field. And so all it's saying is there's more energy in the larger scales, which is well known, and then you have this drop off of energy at these smaller scales. And so this is what a typical power spectra should look like for the vorticity field. And the methods look very similar for the forecast. There's not a big difference in what these power spectral plots look like, and which is good. That's kind of what you'd expect, because these are 24-hour forecasts, and so they're kind of ignoring some of the negative aspects of data simulation, meaning some of the imbalances that are introduced when you update variables in our system. And so this is providing a climatology of what we're after. And then what I'm showing in this slide is if I perform the same calculations, but for posterior members for the ENKF and the particle filter. And the red is the ENKF, the blue is the particle filter. And what stands out here is how much more energy there is in the smaller scales in the ENKF posterior members compared to the particle filter members. Both of them have spuriously large energy in these scales. The ENKF is much larger. And so let's take a look at why that's happening. And again, one thing I should note here is this is happening at wavelengths that are about 150 kilometers or less. And that corresponds to the wavelengths of weather features that are not necessarily depicted well by observations that we have. And so what I'm going to show here is if I took all the vorticity values for my members and I just filtered them out. And so I got rid of wavelengths that are bigger than 150 kilometers. And I plot the vorticity at 850 millibars for wavelengths 150 kilometers and less, and compare them to the GFS analysis that's also been filtered. I'm showing one case here for Hurricane Maria, right before it made landfall in Puerto Rico. And the black lines are showing the values for the ENKF analysis. And these contours are showing the filtered vorticity fields for ENKF forecast members. So these are 6-hour forecasts, and they're the prior members at this time. And here's the same result for the particle filter, and they look quite similar for the priors. But then once you use those priors as the input for data assimilation, the ENKF performs a much different update to the smaller scales in the particle filter. You essentially see this increase in energy going from the prior to the posterior because, again, you're doing something similar to what I showed in that ranking vortex demo. You have these set of vortices that have these position anomalies, and the ENKF has a hard time handling situations like that because of the non-Gaussian error distributions that they pose. And so what happens is you get a partial update of the vortices, which transitions into an increase in energy in the smaller scales, which is pretty interesting. And the particle filter does not have this issue. And so this is for the posterior members. And then when you run a 6-hour forecast from that, then all of the small scale anomalies in the ENKF just propagate away as gravity waves, and so you don't see them anymore. And whereas particle filter looks, has a nice smooth evolution with time. And then this is very, very evident in the variance. If you calculate the ensemble variance in the vorticity field for the ENKF and particle filter, you see this jump, or this dip, I mean, in the variance in vorticity for the ENKF, which corresponds to that adjustment period. And the particle filter has this nice quasi-linear evolution of error with time, whereas the ENKF has this 6-hour adjustment before it starts to increase again. And so this is a common thing to see in various ENKF systems. For example, I've seen this before in the UK Met Office's ensemble system for tropical cyclones as well. And it's really explained by the fact that this Gaussian filter struggles with these scales of motion that are not constrained well by observations. And so I found that to be an interesting result. All right, and so since we're at my stopping time, I'm just going to quickly summarize. Formulating particle filter algorithms that work well for high-dimensional problems is a pretty active area of research. This paper right here summarizes some, but not all, of my recent changes to this filter. I should have a couple more papers coming out soon, including some that summarize the findings from this HWRF regional modeling experiment. And really, this regional experiment has been pretty encouraging so far. It's our first test of applying this method for a synoptic scale NWP problem, and there's large room for improvement. And so I see this algorithm as being rather primitive. There are a lot of areas that can be improved, so I think this is pretty exciting. And I also want to mention that there are some operational centers that are already exploring the use of particle filters for NWP, including Roland Pothouse Group. And so it's an exciting time for particle filters for really big problems. And I'm gonna leave you with this last slide, which is some outstanding questions going forward. One is we have all of these cloud-affected radiance measurements that we're ignoring during data assimilation for tropical cyclones. Can we get around some of these issues with particle filters? Also, this has been all those experiments so far have been done using pretty small ensembles. I'd like to see what the impact is of using much larger ensembles with particle filters. I have a grad student right now who's experimenting with different types of non-Gaussian approximations for measurement errors, and so it'll be interesting to see what that looks like in particle filter frameworks, since it's quite trivial to use different forms of measurement errors. And also, I'm going to just mention this last point right here. What is the best way to formulate localized particle filters? I really don't know the answer to that question, and I wouldn't say that the method I'm using right now is the best. I think there's definitely some room for some better ideas in this localized particle filter idea. And with that, I unfortunately cannot take any questions since I have to run right now. But thanks for your time, and if you want to contact me, just send me an email. All right, thanks.